Welcome to the Deep Dive. Today, we are taking a deep dive into something really fundamental. It's all about how things move and change in the world around us.
That's right. We're looking at two core ideas: gravitational potential energy, let's call it GPE, and kinetic energy, or KE.
These sound a bit technical, maybe, but they're actually key to understanding, well, pretty much everything that moves.
Exactly.
Right.
From, an apple falling off a tree right up to launching massive rockets into space, it all comes down to these energy types.
And together, GPE and KE, they're called mechanical energy.
Yep, mechanical energy. And the important thing right off the bat is that we measure both of them using the same unit.
Ah, the joule.
Joule it is. Whether energy is stored up or making something move, it's all measured in joules. Keeps things consistent.
So our mission today is to really unpack these, not just the definitions, but how they actually work in the real world.
And maybe see some surprising connections along the way.
Okay, let's start with GPE, gravitational potential energy. So this is basically energy that's stored up, right?
Exactly. It's stored because of an object's position. Specifically, its height above, well, usually the Earth's surface. Think of it as energy just waiting.
Waiting to be released.
Precisely. You've done work against gravity to lift something, and that work is stored as potential energy.
Okay, so what determines how much GPE something has?
Two main things. First, how heavy the object is, that's its mass.
Measured in kilograms, kilojoule.
Right. And second, how high up it is. Its height measured in meters, MPa.
So if I lift, say, a feather just a little bit, that's not much GPE.
Hardly any.
But if I lift a really heavy box way up high.
Now you're talking serious GPE. Lots of stored energy there. Mass matters, and height really matters.
Is that it? Just mass and height?
Well, there's one more piece. It also depends on how strong gravity is pulling down. We call this the gravitational field strength.
Little g.
Little g, exactly. Here on Earth, it's roughly 10 newtons per kilogram. We often just use 10 in kilogram to make calculations easier.
So wait, if I was on the moon where gravity is weaker.
Good point. Your g would be much smaller.
So lifting the same box to the same height on the moon would store less GPE.
Much less. Because the potential to fall, the pull downwards, is weaker. Makes sense, right?
Yeah, it does. So how do we actually calculate it? Is there an equation?
There is, and it's quite neat.
Yeah.
GPE equals mass times g times height.
GPE equals NEE.
That's the one. Mass in kg, around 10 kg on Earth. Height in meters. And the answer comes out in
Joules.
Joules it is. And you can even rearrange that formula. If you know the GPE and the mass, you can figure out the height.
Useful. Okay, I think I'm getting the basics. But I remember something from the source material about GPE being relative. What does that mean? Like height relative to what?
Yes, that's a really important subtlety. GPE isn't an absolute value. It's always measured relative to a chosen 0 point.
A 0 point, like the floor.
Could be the floor.
Yeah.
Or it could be the top of a table.
Right.
Or the ground outside. You, the person doing the calculation, get to decide where height equals 0.
So if a book is on a table, its GPE is different if I measure from the floor compared to measuring from the tabletop.
Exactly.
Huh.
Relative to the floor, it has a certain amount of GPE. Relative to the tabletop, its height is 0. So its GPE relative to the table is 0.
Okay. Why is that useful? Seems confusing.
It's useful because we often only care about the energy change during a specific event. If the book falls off the table, only the height difference between the table and the floor matters for the energy released in that fall. The energy it had relative to the center of the Earth doesn't really come into it for that specific action.
Right, I see. It lets you focus on the energy relevant to the situation, like the bungee jumper example.
Perfect example. When they jump, their height decreases relative to the ground, so they're losing GPE.
But then the bungee cord stretches and pulls them back up.
And as they go back up, they regain height, so they regain GPE. The energy is constantly changing form, but GPE is tied directly to that height.
So GPE can go up and down depending on position.
Absolutely. And think about the scale. Lifting a can of soup, maybe 1 meter, tiny GPE.
Okay.
A pole vaulter at the top of their jump. Much more mass, much higher up, significantly more GPE stored there.
And a space rocket. Huge mass going incredibly high.
Staggering amounts of GPE being stored as it climbs against Earth's gravity. That's the potential energy it needs to reach orbit.
Okay, so GPE is stored energy waiting because of height. But what happens when that waiting is over? Like when the bungee jumper falls or the rocket engines fire?
Now we're talking about the energy of movement. That's kinetic energy, KE.
So anything that's moving has KE.
Anything at all.
Yeah.
If it has mass and it's got velocity, which is basically speed in a certain direction, It has kinetic energy.
Right. So KE depends on mass, again in kilograms.
Yep, mass is still important. A heavier object moving at the same speed will have more Ke. Think about a truck versus a bicycle.
Makes sense. And it depends on velocity, you said. Speed. That's meters per second?
Meters per second, correct.
Yeah.
But here's the crucial bit. The relationship isn't straightforward like with GPE.
How so?
It's in the formula.
Yeah.
Kinetic energy equals 1/2 times the mass times the velocity squared.
KE equals 12 millV squared. Okay, half mv squared, why the half?
The half comes from the derivation using calculus, essentially how work relates to changes in speed. For us, the key thing isn't the half so much as the v squared.
The velocity squared. Okay,
Yeah.
so let's unpack that. This is where you said it gets really interesting.
This is the game changer. Let's think about mass first. If you double the mass of a moving object, what happens to its Ke?
Well, the formula is half mv squared. So if m doubles, the KE just doubles.
Exactly. Double the mass, double the kinetic energy. It's a linear relationship. Simple enough.
Okay, but what if you double the velocity, keep the mass the same, just go twice as fast?
Now you're squaring that velocity term. So if velocity doubles, v becomes 2v. What's 2v squared?
2 squared is 4. So 4 times v squared.
Precisely. Double the speed and the kinetic energy increases by 4 times.
Wow. Okay, that's not intuitive. 4 times.
4 times. And if you triple the speed,
3 squared is 9. 9 times the KU.
9 times the Ke, it climbs incredibly fast. That velocity square term absolutely dominates the kinetic energy equation.
So that's why speed is such a huge factor in safety, like with cars.
Absolutely. It's the physics behind the phrase, speed kills. A heavier car has more Ke, yes, but a faster car has exponentially more Ke.
Which means it takes much more distance to stop, and if there's a crash.
The amount of energy that needs to be dissipated, turned into sound, heat, damage is vastly greater. That's why small increases in speed limits can have surprisingly large effects on accident severity.
Looking at the source example, a car, 2,000 kilograms, moving at 20 meters, that's pretty fast, like highway speed.
And it has a huge amount of kinetic energy because of that 20 meters squared in the calculation.
Yeah.
Compare that to, say, a bicycle moving much slower. The difference in Ke is enormous.
It applies in sports too, right? A fast bowler in cricket or a pitcher in baseball?
Definitely. The speed they put on the ball is what gives it so much kinetic energy, making it hard to hit or catch. It's much more about the velocity than the relatively small mass of the ball. That v squared is everywhere in motion.
Okay, so we have GPE stored energy from position, depends on mg and h, and KE energy of movement depends on mass, and crucially, velocity squared. How do they, work together?
They're constantly swapping places. And this exchange is governed by one of the most fundamental laws in all of physics.
Don't tell me the law of conservation of energy?
That's the one. It basically states that energy cannot be created or destroyed, only changed from one form to another.
Never destroyed, just transformed.
Exactly. The total amount of energy in a closed system always stays the same.
So when I lift a ball, I give it GPE. When I drop it.
As it falls, its height decreases, so its GPE decreases, but it picks up speed, so its velocity increases.
Meaning its KE increases?
Right. The GPE is being converted directly into Ke just before it hits the ground. Pretty much all that initial GPE has transformed into Ke. Maximum speed, minimum height.
Like the roller coaster example, high up on a hill.
Maximum GPE, very little Ke maybe if it's just starting.
But it zooms down the slope.
GPE converts rapidly into Ke. At the bottom of the dip, it's got minimum GPE, but maximum Ke, it's going fastest there.
Yeah. And as it climbs the next hill,
that Ke gets converted back into GPE, slowing it down as it gets higher. It's this constant back and forth trade.
But wait, roller coasters eventually stop. If energy is never destroyed, where does it go? It can't just disappear.
Excellent question. It doesn't disappear, but it often transforms into forms that aren't useful mechanical energy anymore. Think about friction.
Like the wheels on the track and air resistance.
Exactly. Friction generates heat. Air resistance also generates heat, very slightly. And there's sound, too, the rumble and whoosh of the coaster.
So the Ke is turning into heat and sound?
Mostly, yes. Thermal energy and acoustic energy. The total energy is still conserved, but the mechanical energy, GPE plus Ke, gradually reduces as it gets lost to the surroundings as heat and sound. That's why the coaster can't keep going forever without another lift hill.
Same if I slam on my bike brakes. The bike stops, so the Ke goes to 0.
So where does it go? Your brake pads get hot, right?
Yeah, sometimes really hot.
That heat is the kinetic energy transformed into thermal energy, plus a bit of sound, maybe a squeal. Energy conserved, just changed form.
So understanding this conservation idea lets us track where energy goes. If a car crashes,
The KE has to go somewhere. It goes into deforming the metal that takes energy plus making a lot of noise and generating heat in the impact. Nothing is lost, it's just redistributed, often destructively.
it really puts the scale of energy into perspective. I remember that ranking activity from the source materials, pressing a computer key.
Tiny, tiny amount of energy. Microjoules, maybe, a single heartbeat, also very small.
But then you look at stored energy, a chocolate bar.
That's chemical potential energy, but it represents a surprisingly large amount of stored joules that your body can convert.
And compare that to driving a car for 80 kilometers.
Huge amounts of chemical energy in the fuel being converted into kinetic energy, overcoming friction and air resistance, generating lots of heat. The range of energy scales we deal with is just immense.
And GPE and KE are the big players in the mechanical world, the energies of position and motion.
Absolutely. If you can track the conversion between GPE and KE and understand that some always gets lost as heat or sound due to friction, you can pretty much explain how any mechanical system works.
Hydroelectric dams.
Water stored high up, GPE falls, turns turbines, KE, which generate electricity, classic GPE to KE conversion,
A pendulum swinging.
GPE at the top of the swing, KE at the bottom. Each swing is slightly lower because a tiny bit of energy is lost to air resistance and friction at the pivot, mostly as heat.
So for anyone listening, especially, students getting to grips with this, what's the key takeaway?
Practice using the formulas. GPE, MO, MEH, and KE equals 12 mV2. Know what each letter stands for in the units kilograms, meters, meters per second, newtons per kilogram.
And use joules for the answer.
Always joules. And get comfortable rearranging them. Sometimes you know the energy and need to find the height or the speed.
And remember that conservation law, energy changes form, it doesn't vanish.
That's the bedrock principle. If you understand GPE, KE, and conservation, you basically unlock the secrets of motion. Hashtag tag outro.
So GPE and KE, they sound simple, maybe, but they really are the building blocks for understanding why things move, how powerfully they move, and where that energy goes.
Absolutely. It's not just textbook physics. It's the explanation for everything from a bouncing ball to the complex machinery that powers our world. Seeing energy as this constant transforming quantity is key.
Okay, so since energy is always conserved, it just changes form. Let's leave everyone with a final thought to chew on.
This is good.
We talked about the KE of a car, but think bigger. Think about a massive space rocket blasting off. It gains incredible KE. But then, as it needs to slow down to enter orbit, what happens to all that kinetic energy?
Where does it go? And bringing it back down to Earth, what's the biggest, most obvious energy conversion you can spot happening around you right now? Maybe in your kitchen or outside your window.
Think about those transformations. Where does the energy come from and where does it end up? Keep looking for those energy changes.